streaming in. I think we can start now. So the purpose of today is to explain as clearly as possible what is the organization of the class. The content of the class, I think, is going to be very, very quick. I don't to explain. I don't think that will require much time. I'll just show you the class schedule, and you will see whatever we will cover. But the class organization is really what I want to describe to you guys today. So the idea is that the class is organized using challenge-based learning. And I call it my challenge-based learning because, of course, this is a teaching framework that we have been developing for the past 4 or 5 years. Right after, probably 4 years. So it's been an evolving learning experience. And there are many TAs and many students that took my classes. Okay, a relative large number of students that took my classes, and I learned a lot from how the student interacted with the class material. So let's describe this today. How is the class organized? Some facts, some Q&As, and then I'll leave you with some slides on the pedagogy of the class, but I will leave them in the presentation. I will not present them directly. And after that, we can decide based on people's background if you want to do a quick refresher of data science. Okay. So usually people refer to this type of student-centric teaching methodology as challenge-based learning, CBL. So if you do a quick Google search, you will find different ways in which people teach classes in this framework. So the idea is that we want to stimulate teamwork. This is one of the things I think that the students, they never get to experience until it's too late. That is, until they graduate and they go to work. It's very rare for students to work in group. Working in group is very, very difficult. It requires a lot of energy spent in aligning people. So the class is focused on group learning. Also self-learning. That's also something that it's very important nowadays. So I will give you some hint or some introduction to the material that we will cover in class, and I will expect you guys to be able to go and research the material independently. Of course, digital fluency. I will expect you guys to use generative AI tools for all the assignment in the class. There is no midterm and there is no final. Everything that you produce, I will assume that you run it by generative AI. There are going to be a lot of class presentation because it is important to articulate ideas clearly. And then we will always prefer solutions that are creative over everything, right? So even if, let's say, if you have 2 paths, one that involves an extensive simulation and running and training a model for 3 days, or spending your time working on some creative idea, we will always prefer creative ideas. Okay, so I will tell you now how the class was run. If you saw the syllabus on E3, then you will already have seen part of this. So the idea is that there is a nice link here that describes in a lot of detail how the class is run. Okay, so we make an effort. We make an effort in this document to explain all the possible details of the class, so that if you are curious about how a certain grade is evaluated, you can go check there. The point is that some of the details of how the final grade is obtained are a little bit complicated, not complicated, a little bit laborious. There is a little bit of there's a bit of details there which is not relevant to the class today, but just to let you know that everything is explained there in case you have any questions. And if you don't find a question, this is a comment link, so you can leave a comment on the documents and I will address it. And the idea is that every 2 weeks you will get a challenge, and you will try to solve the challenge in a group of 5 or 6 people. Okay, so collaboration will be the most important thing. Okay, whatever you do for this class, you will do it in a group. There is no work that you will do alone. Okay. Then also after the challenge, you will submit the material, and the material will be reviewed by other students. So also the amount of influence that I have on your grade is somewhat shared with the other people in the class, so that you will not have to present the material to me. you will have to present the material to the other students in the class for the most part, so that you will have to own your communication to not be targeted at the professor, but to be targeted the audience of the students that participate to the class. Okay, that's it. Then there's going to be a final project, of course. And for the final project, will count for 40% of your grade. And in that case, we'll just be focused on creativity. Okay, so the last project is a very free assignment, and we will just expect you to be very creative. Good. Now, there are going to be 3 phases to this. So phase 1 will starts now, and it will end at midterm week. Phase 2 will start after midterm week, and it will end, let's say, a month before the grades are due. And then phase 3 is the last month of the class. Phase 1, we will randomly assign you to groups, and you will be asked to work on the challenge with a group of people who is randomly selected. Okay? That's very difficult, and it's very discouraging, and this is the hardest part of the class, but it's necessary because the classes are run online. Okay, there is no physical presence, and yet I want you guys to get to know each other and experience what it means to get together with a group of people for 2 weeks and figure out how to work together in groups for 2 weeks. Okay, and so this first part is the toughest part of the class. It will count the least over your final grade. But let's say if you go through this first phase, then you will be ready and set for phase 2. In phase 2, we will have a set of group leaders, and the group leaders will decide who to put in their team for phase 2. Okay. We will release after midterm week. We will release sort of a profile of the students. We'll discuss this later. And so, if you have, I'll come to the question in chat in a second, right? So if you have met during phase 1 the people that you like, you will just message them and be like, "Oh, let's form a group together." If you haven't met all of the people, let's say if you're missing some specific capabilities in the team, you will have a sort of a roster of the teams, and then you will decide how to form the groups, and then you will do the second set of challenges with a group that you choose. And then for the final project, you should know exactly the people that you want to work with, and it will be the last push, the final month, something creative to do together. Okay, let me come to the question in chat. Somebody is asking, yeah, so for the first phase, you will have a new group of people for each challenge. Okay, so the TA will have a nice file online, a nice Excel file. It will have the challenge number 1, 2, 3, and you will see the student ID number, and the student ID number will bring you to another Excel file. On the Excel file, you will have the contact of the person in terms of their email or their line ID or their Slack ID over which you will want to communicate with them. Nafal, can you pull quickly the file from last year so I can show the students? So this is also something that we try to do. So there is a certain anonymity in the way you participate to the class, okay? And we sort of want to allow people to not to fully reveal everything about themselves, right? So if somebody gives you an email account and they're going to work over their email account, you will not need to know their gender, where they're from, what they look like, right? So it's something that we try to foster. Okay, so Nafal is going to share now a file in chat. You can click in and you will see what the file looks like, okay? So we'll ask you to share some information just to make sure that you can contact each other. And we will use the student ID, assuming that the student ID is semi-private. And after that, you will communicate for the challenge. Of course, any question you ask in chat or you unmute and you ask me. Okay? Back here. So again, why do we have this organization? Which is, again, it's a little bit complicated, but we think we have tried to fine tune things so that we achieve the goals that we believe are important for this class. So as first one, you get to know each other. And after the challenge, you will be asked to rate your team members in terms of a certain role and performance. We'll explain it later. So the phase one, it's sort of for you guys to get to know each other and to communicate to the rest of the class what is the role that everybody takes into a challenge. And phase two, we're going to have group leaders. And what we expect in phase two is that by the time you get to phase two, then you understand that the composition of the team for the challenge should not be based on the people that you like the most or your roommates or your friend, but you really need to have complementary capabilities. Okay, so you need, when you work in group, you need somebody that takes decision and keeps people accountable for the work that they do. Then you need somebody which is very good at presenting the material so that they can communicate effectively to the rest of the class what you guys did. And then you need somebody that is good at writing code, and then you need somebody which is good at giving the theoretical foundation of the work that you're doing. So by the time you get to phase two, you should have understood how you should compose the team, what type of team you should choose, so that you can have the best possible performance. And then phase three, it's the final output. So just to demonstrate sort of to yourself that you can not only work together on a challenge which is given you by the professor, but if you have to be creative with this team, then you can also do that. Very good. Now, in terms of evaluation, as I said, there is a certain effort in the class to take the professor away from the center of the class, right? So again, 2026, right? The professor should not be here, should not be the center of the attention of the class. What he says should not be the gospel that everybody listens to. You know, I think it's important that you guys realize that most of the times when you do something, you don't have to present to a single person that decide the fate of your life, but you have to present to a group of people that you are trying to align toward the vision that you have, right? Towards something that you think it's important to do. So the evaluation, right, will be, most of the evaluation will be provided by the other students. Of course, there is a lot of risk in this, but it's also something that I think it's what you will observe in real life, right? And when you have a job, you do a job with a colleague, you present it to your boss, you present it to the other people in the organization. It is your responsibility to communicate to a group of people what is the relevance of what you did. Going back to this, so for phase one, we will have intra-team evaluation and cross-team evaluation. So intra-team evaluation means that you will receive a form, which is a Google form. In the Google form, you will say these are the people in your team. How would you score them? We're going to get to this later. And then you will receive multiple folders, let's say 3 folders. In each folder, there is the challenge material from one of the other teams, and you will be asked to score what this other team did. In phase 2, you guys will have chosen with which people you are teaming up with. Okay, so the score that you will receive will be shared equally with all the members in the team. Okay, so in phase 1, it's possible that somebody decides not to work, and so they will get a portion of the score for phase 1, which is proportional to the amount of work that the other people in the team said that these people did. Okay, in phase 2, you decided to be in the team, so everybody will get the same score in the team. And in terms of scoring, again, our effort here is not to give grades to people or pretend that we can really understand what is a person's ability in 12 weeks. But what we think it's important that people realize that they have to take a certain role in the team. And the role that we have decided to sort of group people by will be leader, thinker, and doer. Of course, leader, there is no particular, let's say, moral connotation of being a leader. For us, a leader is a person that is focused on organizational skills. So they take the challenge. They say, I think this part is going to be done by this and this and this guy. This is how we're going to divide the work. This is how we're going to talk. These are the deadlines that we have. These are the objectives that we're going to try to achieve together. So this is the leader. Then there is the thinker, which is the one that steps back from the organizational skills and just sits down and try to come up with new ideas, understand what is the theory behind a certain challenge. And then there is the doer, which is the guy that usually sits down and writes all the Python code, right? So he's the crazy guy that is there with Visual Studio Code and Copilot and a set of headsets and 3 Cokes, and he's just coding away, right? So we're going to ask you to score people on these 3 roles and tell us what is the percentage of effort that they do. Good. Again, it's just for the purpose of this class. We think that this type of classification of the students, it's sufficiently useful, okay? That it's a good way to pick people to be part of your team. The cross-team evaluation, you will be asked to submit a written report, a video report, and the code base. Of course, we expect you to use GenAI for all of this, okay? So there shouldn't be let's say, even if the volume of what you submit is sort of large, we don't expect you to have a particular, to struggle to provide this material. Then you will submit only 3, and then this material will be given to a subset of the students, and a subset of the students will be asked to score your submission. And how is the score done? The score will be done with this method which we call overranking. And let me explain what is the logic to you, so that from the logic you will understand why we decide to go this way. So the first year we just let people give score between 1 and 10 to the teams, and it happens often that everybody will give 10 to all the teams, because in a sense students don't feel bad. Students feel bad in giving a low score to some teams, right? So they will not want some of their friends or colleagues or schoolmates to get a low grade because of their responsibility, right? So they give a 10 to everybody. So then it's like, oh, okay, so then now we force them to rank people, to rank the teams, so that they have to rank 1, 2, and 3, so that from the ranking, we can then obtain a score. And then people complain that if you are forced to rank, then you don't have enough granularity to distinguish, let's say, submission 1 and 2 and submission 1 and 3, right? Let's say that 1 is the best, 2 is the best submission, then submission 1 is slightly worse than 2, and then submission 3 is really bad. So you will want to have enough granularity in doing this. And so what we did is we come up with this overranking system that we have. So you'll be asked to give a rank, let's say 3 submission, in a scale between 0 to 10. Okay, 10 will be the best submission. 0 will be if the submission is completely empty. And the idea is that you will place things so that the rank is relative to the performance. So, for example, if we said submission 2 is the best one, you give it 10. Submission 1 is slightly worse than 2, but submission 3 is much worse. So you will give, for example, to submission 1 and 4, and to submission 3 and 8. So it's clear that the rank that you give is 1, 3, and 8. So you have some granularity in describing how the 3 submissions differ from each other. And then, of course, it's easy for us to convert this into a score between 0 and 100, based basically on the relative difference in the rank. Okay, it's a little bit complicated. You will not notice this, right? I mean, it's not something that will affect you. You will just put numbers between 0 and 10. You will not without repetition, and then you know that this is a relative ranking, and then we'll convert this into a score. Final grade, phase 1, 25%, because as we said, there's a lot of randomness in your performance of phase 1, and we don't want people to be too concerned about this. If you end up in a bad team, sometimes it happens. Some people don't work. I don't want you guys to get upset. Just remember that this is not going to count much. It's going to be a great experience, but it's not going to count much toward your toward your final grade. Then 35% is phase 2 and 40% is phase 3. So if you do a very good final project, which you will be able to do because you would have got to know most of the people in the class. So you would have figured out how to navigate the group membership so that you can get the best grades, then you will get the best grade in the class. Okay. So usually the grades of the class are relatively high, right? Because I know that the class it's very painful from the perspective of the randomness, right? So there are many skills that are required to get a good grade that leave a certain amount of inherent randomness in them. And so we try to compensate by giving a fairly high grade to everybody so that whatever the variance realization that you observe is not going to affect your grade too much. Good. Let me check chat. So ask something in chat. Is some previous experience with Python required? That's a silly question. Apologies, but of course, everybody's going to use Copilot or Claude or Sonnet or whatever to write Python right now. You guys, I expect you to use generative AI to write code. Right? They will not make you faster, right? Because you still need to understand the logic behind the code, but at least you don't need to worry about what are the options of a certain function, which package does something, which version should I use. So it's especially deep learning. So maybe for machine learning in general, it's a little bit. Let's say the code, it's a little bit harder to write for the generative AI, but when it comes to deep learning, it's so good at writing code that there's no problem. Okay, any questions in chat? Yeah, let me know. I'll give you a couple of minutes to ask questions. Remember to drink water, guys, during class. So now Fal posted the example of the groups, the group formation. So you see that, yeah, let me just share for you guys this. Share this. Share this tab. So you see that here there is the student ID, and then people decide what to put in. Whether they want to put the email address, the Slack, or the other contact, right? So most people use Line. So you see that people decide which name to put. Like we don't require you to. We didn't put the name of the students. Right? We just put the student's ID. If you have some concerns, if I don't want to say anything, right? But if you decide not to put your real name, it's not a problem for us. We will not review this. And also notice that here, some people put the NYSE email. Some people just put you put their Gmail. Not a problem to us. The important thing is that you answer to your emails. And then, of course, yeah, same thing for the data. And then for each challenge, there is the group number. And then you have the people in the team. You see that the teams was usually 4 people. And then, yeah, and then there was a mentioning of who was the leader in which challenge, but that's something that we discuss. We'll discuss later on. Okay. And then let me just show you the document about the document here, the framework that we have. Share. So this document is, we always try to keep this document updated. How do I share? Let me share. Share, comment, oof. Just comment. So this is how everything is organized. Yeah, so here you see that people have left different notes. This is what the report is going to be done. What is the format? What is the review process? Yeah, the different definition that we use for grading. Yeah, so basically we try to be as exhaustive as possible. How many pages is this document already? How many pages is this document? Yeah, so it's 12 pages of document. So we explain everything regarding the class here. Okay. So if you leave any comment, I'll address it right away, of course. Okay, good. Any other question here? So think of it a second. So now Fal is the TA. It's his second time being the TA for this class. Yeah, we're still looking for some QAs, depending on how many people eventually decide to take the class. And yeah, so if you have any questions, let me know. Okay. As I said, the logistics are a little bit complicated at first, but we will remind you everything as the class goes on, and we will tell you, we'll remind you of deadlines and phases and so on. Also remember that, yeah, so everything will be available online. The challenges, we will post them in PDF. Yeah, so the logistics they look a little bit difficult at the beginning, but then you get used to it. Remember, so I don't know if you checked the syllabus of the class on E3, but basically we post all the classes online on my YouTube channel playlist. And you see here that there is, for example, if you look at the playlist on my channel, right? So you see that we have all the playlists for the past classes. So this was the class from last semester. So this was Lab on Python for machine learning, which was the companion of this class that apparently only a couple of you saw. And then if you go to the playlist, there is a playlist for also for Lab on Python for deep learning, right? So if you want to see how the class goes, you see that the background is the same, right? The haircut is the same, but you see that we have all the 13 classes, everything is there. Yeah, so if you are curious about how the classes run, just pick, and you will see that most of the classes are just people presenting, right? This one here is, yeah, here we're doing gradient. Okay, so this is not a class with pure presentation. We try to get class with presentation, but basically, yeah, usually the students are presenting. Yeah. This is my student. This is, so yeah, so most of the class is student presentation. Let me share this. Of course, I'm trying to monetize my YouTube channel. I think I'm very close, just a couple of billions of views away. So if you want to subscribe to my channel, you'll help me on the view of gaining financial independence through YouTube sponsorship. So next time I can tell you about some NordVPN, guys, and you can help me be independent financially and finance my hobbies, my woodworking and 3D printing hobbies with YouTube money. But that's about it. Okay. Any question? Again, I'll give you a few seconds to think about it. Of course, yeah. Submit to the YouTube channel now so that I don't need to remind you later on. Okay. Very good. So let's go back to the presentation. We'll just do a couple of facts, and then I'll ask you what you want to do next. So let's see a couple of facts. FAQs. So why don't you teach Python programming? Okay, so in the past edition of the class, we will take a couple of classes at the beginning to teach Python to people, and we will tell you about memory management in Python, versioning, installing packages, blah, 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 blah. But this is now mostly obsolete, right? So first of all, it's a very high-level language, Python. So when you call a Python function, there are many low-level operations that take place that are completely out of your control. And that's the beauty and the course of Python. Right? It's a beauty because with a couple of lines, you can train a neural network with hundreds of millions of parameters. But of course, as we were saying in the beginning, right, you lose control a lot of the low-level performance of your program, and so the efficiency goes down pretty quickly. But this is inevitable. And when you try to program in Python, usually you write 10 codes, you write 3 lines of codes, and then you go on Stack Exchange and you try to figure out what was the definition of a certain function. and this is not particularly useful. So it's not very pedagogical for me to tell you. Remember that the third option for the layer definition is the activation function, right? That makes no sense. Of course, there is a lot of documentation on Python online, and of course now I expect all of you guys to have tried Copilot or Gemini or whatever, right? So you go to Visual Studio. On your Visual Studio, you integrate your LLM engine that you like, and then you try to go on from there, right? So it's a new way of writing. As I said, it's not more efficient than learning Python from scratch, but this is what I will expect you to do. If you're starting from scratch, you start using the LLM, and then eventually you get better and you get faster. So let me ask you, let's say, what's your Python knowledge level? Between 0 means never used, 10 equal to used daily for 1 hour plus. Tell me in chat, guys, so I get a sense of how much. Okay. See some good numbers. Yeah. Okay. So no 0 so far. I see a 0. Okay. Don't worry. I see 2 zeros. Don't worry. There's space for everybody in class. We don't. You learn one way or another to use this tool. Now the important question: what's your favorite LLM for writing code? 0 is equal to none. Otherwise, by Gemini, Claude, ChatGPT. Let's see how many people go raw in writing Python. Okay. Copilot. There is somebody who really uses Copilot. Yeah. Codex, yeah, Sonnet. Very good. Yeah, so today it's a slow lecture, okay? And also I'm talking a lot, so I'll give you an idea of how I would teach lectures if I didn't use this particular framework that is telling stories, because my brain is always trying to organize things in stories that I can understand. There's a second digit. This. Let me show you this paradox. Okay. So because again today it's a little bit more discursive. So if you look at the statistics on the performance of people using generative AI for coding, we can also discuss the statistics on people using generative AI for other tools, let's say management. You will see that people perceive themselves to be faster when they use. Okay, let me step back. They did a study in which they took some experienced programmers, some middle average experienced programmers, and they asked them to complete a certain set of tasks, and they allow some people to use AIs, and some people they were not allowed to use AI. and they recorded the performance, okay? And they asked them what the perception of their performance was. So the speed at which they completed the task, on average, was the same with and without ChatGPT or without generative AI. Okay, so for an experienced paradox, for an experienced programmer, there is no large difference whether they use LLMs or not. Again, experienced programmers. But they asked them what was their perception, and the people that use generative AI, they had the perception that they were much faster when in reality they were not faster. Okay, so you get the you for sure you have to account for the fact that you have a perception that you're faster when you use the generative AI tools, but then you know that this is some sort of bias because you think that you spend most of the time writing code. So you think if you're not writing code, you think you're going faster because the LLM is doing completion. But of course, in reality, most of the times you're trying to use your brain to understand the logic of what you're doing on that time. And so maybe you're not so conscious of that time. So when I saw the study, I thought about this, which is a sort of it's something that it's a phenomenon that has some echoes of the period that we are living now. Okay, so they call it the productivity paradox of IT. So in the 1980s, people started introducing a lot of computers in the workplace, and people were sure that that there will be a great improvement in productivity of like 10%, 50%, because people know they were using computers, so it was faster to write, you didn't have to print things, blah, 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 blah. But actually, they saw that the labor productivity went down, okay? So they saw that, that this is not what happens, right? You can go through this, right? But what people interpret of this data is that when you use IT, there is a lot of things that need to be reviewed. There were a lot of automatic reports that were generated, and people were still manually going and trying to deal with the output of this system, because the system were not optimized and people did not know how to use them, and things were still evolving, they were changing, and they were unreliable, and so there was a big drop in productivity. And so this is the period in which I think maybe this period has some echoes of what we are seeing now, right? We are seeing that these generative AI tools, they have the promise of improving your productivity when coding, but then actually when you look at the statistics, there is no improvement in productivity. So you wonder what is the reason of this. And one opinion that one could have is that indeed these tools are changing too quickly, right? So people haven't learned how to use code generation that effectively, because every 2 weeks you get a new model, you don't know how the model behaves. And then also there is a lot of code which is being produced now, which is very low-level code, because people don't know how to manage this increased amount of code which is being generated, right? And then you need to have people that review the code which is submitted, for example, on code bases, and you have to figure out, oh, this code is very inefficient because it's generated with AI. And so there is a lot of vibe coding and slop in code repository. And so I think that, I think you will have the chance to experience this, right? So especially for the people that don't use these tools daily, it's a new tool that you have to learn how to use. Probably there is no going back, right? So there's not going to be a period in time in which you don't use some sort of LLM tool for writing code. So it still makes sense for you guys to learn this tool now, but the efficiency of using this tool is probably going to increase in the next year, and hopefully hopefully where there's going to be some substantial increase in productivity. Not in the next decade, but hopefully in the next few years. Okay, good. Let's go back to the slides. So what were we saying? We were saying this. Okay, so it's of course the lab on Python, but there is no Python. Some people joining. Somebody fell off. Okay, then where is the presentation? Is here. So another question that I always ask is like, oh, why do you use Slack? Okay, so Of course, we don't have to discuss why we don't use E3, because if you ever use E3, it's ridiculous. I mean, it's a very inadequate platform for 2026. So this is the team management tool that I use in my lab and for my for let's say for the other organizational teams that I'm part of, let's say the community or the challenge organization or challenge planning or research teams. I always use Slack. I guess that all of you use Discord. Do you use Discord? 0/1. I guess all of you use Discord, and usually mostly for gaming. My assumption is, yeah, see, and I guess you use it mostly for gaming, right? So Slack is like Discord for people with jobs. No. So Discord, Slack is like what Discord people, what Discord users use when they go to work. Okay. Of course, it's a partial tool. We could also use Discord. It's just if you use Discord on your with your gaming friends, I don't want my notification to be confused with theirs, right? So maybe we try to separate your personal life and your working life. Maybe there's some value in there, but also I want you to experience this as a management tool, right? So you can decide to cooperate there. Or usually my response time on Slack is basically instantaneous, right? I'm hooked to Slack. So if you have a question there, I can answer more quickly, even on mobile. And so please bear with me. This is a tool which is very convenient for me. I think it's useful for you guys to try the platform and try to deal with these management tools, which you will use for sure when you go to work, right? Some other, maybe some other platform. Maybe you have to use SAP or something else or Teams. But basically, all these tools they're very, very similar, right? So there are going to be different channels. On the channels, you put all the people that are on a certain project. If you need to share files and blah 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 notes. So it's just a convenient tool to have, and it's much better than E3. So let's just go there. Sometimes people complain that the challenges are much harder than the topics they discuss in class. Okay, so in my mind, as I said, I'm going to try to minimize the frontal teaching. And when I give you something, when I teach something in class, I will try to give you the introduction to the topic, and then the challenge will be 10 times what I taught in class. Okay, and this is by design for two reasons. First of all, you are expected to go and look for this information for yourself. Okay, this is part of the class pedagogy is to work independently, but also the amount of work should be such that you guys have to separate the work across multiple people. Okay, so that you are a team of people. You need to have the leadership to say, "Oh, the challenge it's so large, it's so extensive. It requires such depth of knowledge that the only way for us to manage it is that we have to separate the work." Okay, so the reason why the difficulty level of the challenges is so much larger than what is taught in class is to force you to do these two things. And of course, it will happen, right? That some people try to skirt the responsibility. They try to do the least amount of work possible because some weeks they want to go home and they don't want to work too hard, or they want to go somewhere, they want to hang out with their girlfriends. So it's natural that people's commitment to the class wanes sometimes. But so you have to. That's why you really need leadership, right? You really need to figure out that if you want to work in group, you cannot avoid having a leader that tells you, that organizes the work, and then you have to be held accountable for the work that you were assigned, right? And so this is very tough sometimes when people come and say, "Oh, the challenge was so difficult. My teammates were not working hard." Unfortunately, it will happen, and it's unfortunate. It's an experience that we wish you guys don't have, but it's inevitable. I think it reflects what you will experience in your work, right? So the reality of life, I think, is this one. So some people complain about my accent, and especially the speed at which I talk. So unfortunately, I talk a lot. I have a lot of meetings in my calendar, and I speak with international English, meaning that people. I usually speak to people for which English is a second language, and so bear with me with my Italian accent. If I speak too fast, let me know. Always try to turn on the subtitles in the call if you're having difficulties, and otherwise, yeah, apologies. And remember, there is no requirement for you to attend the classes, right? So if you think you prefer to study by yourself, you don't want to be in class, you prefer to open the slides and read the slides by yourself, look some other professor. Of course, this is perfectly understandable, right? I mean, you should attend the classes when you have to present. Otherwise, your team will be penalized by the fact that they have to present material, they have to prepare a presentation that was your responsibility. But when it comes to frontal teaching, you can do whatever you want, of course. Yeah. So a lot of people then have difficulty with the teammates. This is actually the biggest common experience about the students. Phase one is very tough. Some people, phase one is very tough because some people know that they will drop the class by the midterm, okay? Because maybe they get some bad grades along the way. They get some feeling that they should focus on their classes, and so they will stop answering and they will stop being active, which is very unfortunate. Because when they do so, they don't tell us. So we keep assigning people to the teams, and then somebody says, "Well, but my teammate said they will drop the class." I apologize in advance. It's something that we try to obviate as much as possible. We keep telling the students, "Oh, if there is somebody that is not active, let us know so we can remove it from the assignment of the class." And some people are just not particularly responsible regarding their schoolwork. They don't have the feeling that by not letting us know that they are not participating, they are hurting the rest of the class. I think it's not a big problem in general. It's just that if it happens to you, then it's a very negative experience. Okay, it's like being run over by a car. I mean, okay, it's like I don't know, dropping something precious. Let's say let's not be too negative. It doesn't happen often, but if it happens to you, you're really pissed. So it's something like that. Okay, so we try to obviate a problem. If it happens to you, apologize in advance. Let the TA know. We will reorganize the classes. And yeah, of course, we try to give you the best experience possible in the class. So we try to do our best there. So then there is the worst case in which not only you are so unlucky that you get one person that doesn't participate, but nobody in the team is actually working or talking. But it means that you're being very unlucky. Then you let the TA know. The TA will just basically the TA is the power to do whatever you want, right? So we will try to reach out to some other team and be like, okay, there is this guy which has been super unlucky, has been stranded, and we will do the best that we can to give you a good experience, okay? And for me, this is like being hit by a lightning strike twice. So I don't expect that more than one person will have this very negative experience in which more than one person in the team goes silent. If it happens to you, again, apologies in advance. We're trying to do our best. But for the others, hopefully you don't run into this. Very good. Again, I'll give you a chance to ask some question. Any question? I'll give you a couple of minutes. So let's do this. So after this set of slides, I share this set of slides. Now there is set of slides, there are some discussion over the AI era, right? The rise of generative AI, but I'll just leave it there for you, right? So just go through this set of slides if you want to understand why we are trying this. I just want to let you know that there is a growing movement toward this type of teaching framework in which students, they learn independently. Of course, the role of a professor has changed a lot in the last years. And there is basically no I think there is, in my opinion, there is no substantial benefit for you going to class, looking at the professor presenting the slides. It's the real learning should be with respect to the motivations, why we live the life that we live, why we care about the things that we care about, how do we see the students, what do we hope for you guys, and these are all parts of our job that are not quantified by the number of slides that we have in the presentation, or the number of homework that we give you. When it's a very tough moment, I think, for professors to have to adapt to this reality, right? Where we want to convey something meaningful to students, but it is very clear that the usual way in which we do this, the way in which we used to do this, is no longer there, right? So, for example, if you had to come to me 10 years ago to class, I will be on a blackboard writing down equations, and through that act, you would have still understood that I care for the students. I wanted you to learn something meaningful. I want you to have a successful life, which you take the knowledge that was taught to me and you use it for something useful. And because there was a different moment in time. But now, if I did the same, I would be doing you a disservice, because when you go to work, you will have a very different working environment, where what work is very, very different from 10 years ago. And the pace at which knowledge is to be processed and manipulated and acted upon so much quicker, that a person teaching you something at the board is no longer useful. And so it's very difficult for me to still convey what are the values of the job that I try to live by. So it's very difficult. So this is part of so this is the rest of the slides, okay? Now, in the spirit, we can do two things, right? We can do a couple of, let me just show you one more thing. So the slides, if you want to know the content of the class, it's all here, right? So you're going to be following these slides from Harvard. Just the topic of the class are really the basic of deep learning, right? So if there is going to be some frontal teaching from here. Of course, we start from the multi-layer perceptron. Then we will do backprop, gradient descent, SGD, then neural networks, then convolutional neural networks, then some MLP, some NLP, some natural language processing, and so on and so on and so forth. Okay, so if you wonder what we're going to do, these are the slides from 2022. We can also go to the slides for 2021, which have a little bit more presentation there. So I will go through these slides sequentially. Okay. So for example, these are the 2021 slides. Okay. So for example, we are going to start from maybe this is all recap, right? So we're going to start from multi-layer perceptron, right? So you just click here and where are you? Patient, Synapse basics. Okay, so basically, you will just go here. There is the PPT, and you will know week by week which slides we're going to do, and you can just follow along. You can review the slides before class. You can review the slides by yourself. The usual stuff. So the topic of the class, in my mind, are very, very clear. So increasingly, there are specialized architectures for deep learning that one should know, and they describe a specific use case. For example, I expect you guys to all know what is a neural network. So you have an idea of layers and an array of perceptor activation function. Then you do backpropagation. Very good. Then convolutional neural networks are a structure that generalize convolution operators. And so these are often used for images, for spatial data, for time series. Then then we're going to go to recurrent neural networks, RNNs. So this is a sequential model. Again, so this is sort of a deep learning generalization of what a filter is, what an LTI filter is. GRUs are expansion of this idea to longer-term memories. And then eventually we're going to do some language modeling, right? So the great revolution of machine learning in these past years has been understanding that if we move the representation of human language to some space, to some semantic space, then we can operate over this semantical representation with mathematical operations in a way which is very, very efficient as performed by computers. So a lot to do there. Then we're going to do some variational autoencoders, some generative adversarial networks. But basically the topics, in my mind, the topics will all be things that you have seen in your normal parlance or in your everyday life when people talk about deep learning. Okay? So personally, I will not spend too much time on describing the topic of the class. You go to these web pages, you see what the slides are. You know that every 2 weeks there is going to be a challenge which is related to some of these topics, and then the self-learning will start from there. Okay. Okay. So after this, let me give you a chance. What we can do is that we can do many people studied machine learning in the past. Sorry, did you study machine learning in the past? 0/1. By which I say this, right? Usually there is a nice image that people refer to explain this, which is this beautiful image here. What is this image? Come on, I just want an image. Why is it taking so long? This is the longest it's taking me to load an image from the internet. Okay, so usually people describe the difference between deep learning, machine learning, and artificial intelligence as follows. So by artificial intelligence, we say any computer-aided technique that mimics human behavior, right? So for example, people talk about self-driving as being artificial intelligence, meaning that whatever technique you want to use in order to emulate human driving, that will be considered artificial intelligence, AI, okay? So it's it doesn't specify much about the framework in which these algorithms are developed, okay? Now, if we talk about machine learning, then it's clear that something comes to mind to most people, which is dataset, losses, gradients. Okay, so now you are thinking that the algorithms are developed using a certain datasets, which is used to train a set of algorithms using some sort of gradient descent technique. Okay, some sort of optimization technique based on gradients. And when you talk about deep learning, then people understand that the type of algorithms that you are developed are those implemented by neural networks. Neural networks have different architectures. Different architectures are good for different jobs. But now you have a data set, you have a loss function, and you have a neural network. So that what you are training at the end of the day, it's a deep neural network. Okay? So this is usually the distinction that people do in these treatments. Okay? Let me check the chat because it's in the chat. Okay, so a lot of people didn't do any machine. What is it? Maybe 30% of the people did some machine learning. Some other didn't. Okay, so we said that we will teach for 2 hours. Okay, so I'll give you a chance to choose what happens next. So we can start a review. We can start this set of review slides. Okay, I think we can go through this set of review slides. Okay, so of course, if you want to leave, you just leave. No worries. Don't need to discuss it further. I think we do this. We take a 5 minutes break. So I'll see you back at 35. You go drink, you go walk around. You take the time to do whatever you want to do. And then if you want to stay, we'll do a little bit of a review of machine learning. Very, very high level review of machine learning. This comes from a class that I taught last year. And otherwise, I'll see you next week if you don't want to attend to this. Please register on Slack. The link is in E3. Let me post the link here again. Invite people. Please invite people. As I said, I would be very happy if everybody comes over Slack, so I don't have to use E3. I don't have to log into E3 to send you a message, because it's a waste of time. I mean, it takes 10 clicks just to get to an announcement. Right on Slack, my phone very, very quickly. Okay, good. So next week we're going to do the first set of slides on the MLP, on the multilayer perceptron. The set of slides that we're going to do is this one here, and you're going to have the first challenge being assigned, so you can get an experience for that. Just give me a second. Maybe a second. I'll send you the set of slides on the MLP. Mm-hmm. Oh, I was one of my students. I see. I'm just getting older, and you guys are just looking at me aging, and I never see you guys in person. Did you come? Yeah. Did we meet in person? Or? Did you say? Yeah, of course. If you see me on campus, remember this. If you see me on campus, right? That you guys see me, but I don't see you. So if you say hi to me and I look at you, okay. If I look at you and I look confused, remember that it's not my fault. Okay, very good. So if you see me on campus, say hi, of course. If I don't say hi to you, it's because I don't see you. Just a second. I'm looking for. Yes. Yeah, you take 2 courses. You take two courses with me this semester. Please, guys, take 2 courses with me this semester. Just a second. I'm looking for slides on MLP, and I'm blanking out a little bit. Neural networks, neural networks, perceptor, and MLP. Should be the set of slides. Okay, so yep. Okay, good. So next time we're going to go through this set of slides. I'll just tell you now, in case you want to go there. Okay, good. Sorry. Recap. We take a break now until 38 at this point. Then please register to my other class, the numerical methods for machine learning, the numerical space for machine learning. Make sure to sign up in Slack. The link for the joining Slack is there. If you want to know which slides we're going to do next time, it's going to be the first link that I sent here. And I'm going to send you after the class a link with the recording for the class today, the slides that we're going to cover, the plea to join my other class, and the material for today in terms of the slides that we presented, and that's about it. Okay, we take a 5 minutes break. I'm going to mute myself. Any question you're asking in Slack or in the chat, go around, walk, drink a little bit. I'll see you back at 38. Okay. Okay, guys, any questions? Any questions? Any questions? Okay, good. So let's go through this set of slides that we have. Again, this is the longest. I swear, this is the longest talk in one class. Hopefully. Okay, good. So let's do some quick review on the machine learning algorithms. Okay, so this is just a review, right? Because we're just doing this review for the people that haven't done machine learning, and we're just going to see 3 topics. But these 3 topics are sort of the key ingredients that you're going to need to understand. Both the historical basis of deep neural network and also some of the fundamental concepts that we're going to use. Remember that generally we see ML as being more general than DL, deep learning. So KNN, which is a simple regression, which is model-free. Linear regression, which is basically a canonical regression algorithms, and it gives a sort of an interpretation of some of the linear algebra that you saw in the past years, maybe also in your high school. Let's see if you can throw a link there. And then support vector machine, which are interesting because basically they introduce you to the problem of classification instead of regression. Okay, so this is in machine learning there are 2 canonical problems. One is regression, which is predicting continuous values on an order line, and there is classification, which is predicting discrete values, which are not in any particular order, right? But we're gonna get there. And then if we get there, we talk about the perceptron and what a deep neural network is. Let's see. So of course, the fundamental of the revolution that we are seeing in the past years when it comes to deep learning and machine learning and AI, it's all based on the increase in availability of data and our ability to store, manipulate a large amount of data. Again, this is a long, it's a long history that have brought us here. But of course, our ability to reproduce, store, transmit, catalog, collect this data has increased of many folds since probably the 1980s. And so first there is a data mining. So first there is an understanding, right? So there is this plot is from a business perspective, but of course from a scientific or an academic perspective it will be the same. So first thing is to understand what is the question that we are trying to ask. Then you have to collect the data to answer this question. Then once data is collected, the job starts, meaning that you have to clean the data. Okay, so cleaning data is very expensive. If you ever build a data set, then you know that data cleaning is very time consuming. And if you use a data set that has been already cleaned, you should say a little thank you mentally to the people that did the cleaning, because again, I used a lot of time to do it. And then there is data exploration, meaning that people generally understand that data is very high dimensional, and it is not clear to you at the beginning of this data science cycle what are the relevant aspects of the data, right? So there might be some ways of representing the data, some simple analysis that you can do that it will tell you what is the quality of the data you have and where are the patterns of the data. Then there is feature engineering, meaning that, as we said, data is generally high dimensional, which means that you could have each entry in your data set, each time you collect data, you could have hundreds of thousands, millions of parameters collected every time. So usually it is not particularly wise to take the data as it's being collected from the sensors, but you should engineer some of the features which are meaningful. For example, if you took a picture, the picture maybe it's very high resolution, it's in color, but you are trying to recognize handwritten digits, then it's clear that you shouldn't care about the color, and the handwritten digits can be downsampled very, very heavily, right? So you take a picture, you convert it to black and white, and you just crop it around the area in which there is some text. Other example, you record the video, you want to do some lip reading, okay? You want to train a model to read the lips of a certain speaker. Of course, the first thing that you do is that you convert it to black and white, and you just crop the area around the lips, okay? So using all the collected data is usually not particularly smart. What you can do is that you can reduce the data that you want to use to a set of parameters, a subset of the parameters, which is very informative. And this is what we usually call data engineering. Then you build the model. The model will do some of the, it will try to answer what was your original question. In the example before, to translate a picture into text or to translate a video into text. And then you will try to visualize the result in order to see what is the quality of the data, of the prediction which is produced by the model. Okay, so the classical example that we work with in our slides will be the advertising data set, which is data which is collected here during 2013. And basically there is a publicity firm, and they have to decide how to assign a certain budget between TV, radio, and newspaper, and they want to predict the sales of the product. Okay. So in this type of data sets, there is natural asymmetry, which is as follows. Some of the variables are easy to collect, they are easy to control, and they are easy to influence. And there are some variables which are harder to manipulate, which cannot be manipulated, which cannot be easily measured, or cannot be easily inferred. And so the process that you do is to take whatever it's easy in this context, to predict whatever it's difficult. So if we go back to this example, it's clear that the variables under which we have control is the assignment of the budget. And the things that over which we do not have control, that we do want to predict, are the sales. Because first we put the budget, and then we observe the sales. Okay, so there is a temporal asymmetry here that clearly tells us that the interesting parameter for us are the sales, but we cannot observe the sales until we have fixed the budget. So we have to predict how a certain budget allocation is going to produce a certain set of sales. Very, very reasonable. And this is what we call features and response. So the features are the easy variables, and the response is the label that we're trying to predict. There are different words for this. Just be aware that people will call this a response, a label, a Y, an output, and the feature will be an input, a feature, a variable. Yeah, so different vocabulary for this. As we said, these are the X predictors, and this is the Y outcomes. And usually, once we have this, we build a data set of observation. So we build a data set in which we have P predictors that we use to produce the output for one variable. Okay? And we have an observation of this phenomenon. And this is what we call a data set. So as we said, when we talk about ML, we are implicitly thinking that there is a data set. So there is a data which has been collected and compiled into a data set. And then we want to build some machinery on top that will give us, will predict, in this case, the response, even the predictors. The first question that you asked me is like, oh, why don't I, am I limited to only predict one variable Y? My answer is that of course not, but mathematically, you can always break down the prediction of 10 variables into 10 models in which you predict one of the variables at a time, right? So there is not much generality that you gain by considering a different cardinality of the response, okay? Of course, as the number of predictors increases, intuitively the problem It gets harder in a non-trivial way because the input is becoming larger. So there is a larger numerical complexity and memory requirement. So it makes sense for us to consider the scaling of a problem with the number of predictors P. But when we change the variable, response variable at first approximation, right? We could say that the complexity increases by the number of variables that we're trying to predict. So we can consider the simplification in which you will produce a different model for each of the response variables that you want to predict. Again, first approximation. Usually we have x1 to xp, and then we have x1 to xn to indicate the rows of the dataset, and then the outcome will be y1 to yn, when small n is the number of entries in the dataset. And then after we have this, we have to decide what do we believe is the reality of the world that we live in. Okay, we have to say there has to be a relationship between our input and our outputs of the model, our predictors and our response. And what we settle on is to say that there is a deterministic function f, which is controlled by a set of parameters theta that links the input x to the output y by allowing for some noise epsilon, which is independent from x. Okay, very important. Going back to the example before, of course here the sales will also depend on what the heck you're selling. Okay, we cannot abstract away completely from the model the features of what you're selling, how desirable it is, what is the business need of something, what is the novelty of the product that you're selling. But from the purpose of our problem now, these are things that we do not want to consider, because we want to abstract away the meaning of all of it and just focus on predicting the y from the x, and whatever determines y that is not contained in x, we will treat it as an independent noise. Okay, good. So we bet that there is a function f that can capture everything I can capture from x in order to predict y, and whatever cannot be captured, I just put it in an independent noise. But if the noise were not independent, then it means I could have a better f that extract more information on x over y. Okay, so noise is always independent from the f theta of x. Okay, so I think that I can come up with a model f that extract all the useful information from x in order to predict y. Whatever is left in y that is not predicted from x, I'll treat it as independent. This is very ontological, right? You could say that you always call noise what you don't know, what you don't want to add in your mathematical model. Right? So it's philosophically it's something meaningful. Okay, now we have to discuss this theta. What is this theta that we have? We expect this f to belong to a family of functions. Okay, and we expect that this family of functions is determined by a certain set of parameters theta. Okay, so imagine that you have a linear function, and the linear function is y equal to ax plus b. Okay, so in this case, the a is by changing a, you change the mapping between y and x. So you assume that there is a set of parameter theta that changes the behavior of f, and you want to determine this set of parameters. Now, the data set comes in. The data set says that this theta can be learned from a data set of observation that you have. Okay, so now the problem is to use theta, to use the data set t in order to predict theta, which extract all the information from x regarding y, and whatever is left is noise. Okay, very simple equation, but there's a lot to discuss here, of course. Now there is some other assumption, right, which is the fact that in the family of function f, which is parameterized by theta, we also have the exact function that extract all of the information regarding y from x And this is something that we will have to prove in some sense, right? It's a theoretical, it's an assumption that we can have at the beginning. If you will want to investigate this, this is the concept of learnability, and you let me know, and I'll send you a chapter from a theoretical machine learning book. Will explain to you what is the learnability of a function and what is the sample complexity. Okay, so now let's say that we put all the data set that we have and we try to represent it graphically. For simplicity, let's just look at the TV budget. So we plot all the data set as follows. We fix the TV budget row. We look at the variable y, which is our sales, and we just plot this in a two-dimensional plot, and we see that there is a nice pattern. Now x will be the predictor and y is the response. And now we are at the stage of data visualization, and we can try to visualize it. And of course, it seems that there is some relationship that we can infer from this. So what we see is that, of course, if the budget is 0, the sales are 0, or maybe the sales are a certain minimum. And as the budget increases, then we have higher sales. That seems to be reasonable, right? So the average sales increases with the budget. We observe also that there is a certain variance. So the variance increases with the budget. Of course, if you spend 0 money, there's smaller variance because there are fewer people that you can influence. If you have a larger budget, then you're influencing more people. So maybe you're observing a larger variability of the response of the people to this. But there is a story that you can tell from this, and especially you can tell that there is some sort of prediction that you can make, right? Because you can predict that if your budget lays around here, then your sales will lie around here, and if your budget is around here, then your sales will be around there. Easy piece. Now, how can we do the prediction now? There are many ways in which we could go about this. Let's start with the simplest one that we can imagine. And the simplest one that we can imagine is the one that doesn't explicitly fix the function f that we are looking at. Okay, we're going to try to go and produce a prediction with the least amount of assumption on the function that we want to pick in the class of all functions. And in particular, we look at k and n, where k is it's a number, and n is nearest neighbor. So n here is not neural networks, it's k nearest neighbor. So the k nearest neighbor is the idea that if you have to predict something, you will look at the neighbors, the k neighbors of a certain point, and you will have a prediction which is just based on the values of your neighbors. Let's see what is the simplest example here. Remember, this is TV budget, this is sales. The model that we want is as follows. Samba gives us a TV budget. Let's say it's 123, right? And for this number, I want to predict what is the sales. So I'm going to do this. I'm going to plot the points in the data set here on my axis, and with the corresponding sales. And when a budget comes in, I'm going to predict the sale, which correspond to the closest point in the data set to that budget. And I'm going to predict the sales of that closest point. As we said, we go for 123. Let's say that the point is here. We go and we look for the closest budget to this budget, which is going to be this 130. And we see what are the sales for that budget. The sales was 13.5. So we predicted our sales is also going to be 13.5. Okay. So you receive a budget, you go to your data set, you see which elements in the data set had the closest budget to your budget, and you predict the same sale that this point has. Okay, so this is a one nearest neighbor. Okay, you look at one neighbor and you predict the same sales as your closest neighbor. Not very useful. What we want to do is that we want to consider more neighbor and take the average across a larger number of neighbors. Okay, meaning that now if somebody gives me a budget, I look at the three closest neighbor, and I say that the average sale that I have is the average between the three closest points. Okay, so you see here that you have k equal to 1, so the k equal to 1 jumps at the midpoint between the 2 points, because then the closest one goes from the left one to the right one. Now, if we look at the 3 closest one, right, then this value here is the average of this one here. Then here we switch is the average of this one here, then this one here, then this one there. So we have more jumps. But the curve is generally smoother. Why is the curve generally smoother? Because we are taking average across more points, and you know that averaging always smooths out variations, right? So in a sense, it's intuitive. And here we are in the simple example in which we have 8 elements in the data set. So when I fix k equal to 8, for each budget that I have, I take my 8 closest points, and I take the average of those 8 closest points. But since the data set has 8 entries, I always have that the full data set is the neighbor to my points. And so I always take the average of the same 8 points, and the average of all the same 8 points gives you a constant. Right? So this is the pod that you imagine. K from 1 to cardinality of your data set. For k equal to 1, you have this very jumpy behavior. As k increases, the prediction gets smoother, and then you get to the prediction being a constant, which is just the average of the data set. Very good. Let's repeat this with more points on our TV budget, and you see the same story, right? K equal to 1, very, very jumpy. So the prediction is very much dependent on the closest neighbor, so there is a lot of jumping. And then as k increases, you become very, very smooth. And then there is going to be a k where you grow, where your k is so large that you become overly smooth, right? You see that this curve is very, very nice because it really captures the pattern in the sales. You see that when k is equal to 70, then of course here we have flattened down our prediction too much. And you see that the range of prediction that we have, it's let's say between 13 and 25 and 18. So the range of prediction is very, very small. So we are almost always predicting a constant. So we are not really using the information in the data set to do the prediction apart from one number, which is the average sales in the data set. Okay. Any questions so far? Any questions? Any questions? Speed is good.
Teacher, like where can I get this PowerPoint?
It's there. I posted it. Let me post it again. Let me just paste share. I think I pasted it in Slack. Let me paste it again. Okay. Any other comment? Also, this is based. Yeah. It's based on. Let me just put the course, the slides from last year. So I'll put all if you want to do the machine learning, you can take the full machine learning class that we used last year. So if you want to review all the topics in the class from last year. Okay. I'm gonna send all the links after class. Okay. Good. Any other comment, guys? I see a thumb up. Do you have any other comment? Let me check. Okay, very good. So when people do k-nearest neighbor, people think that it's very, very easy. Actually, it gets tricky when you go to higher dimension, right? Because when you're in a one-dimensional space, if you have to find the midpoint between 2 different points in the data set, that's very easy. Just one line. But you can imagine that when you go to higher dimension, finding the minimum distance points gets really, really tricky. And generalizing over higher dimension gets pretty nasty. Because, yeah, you can see here the example of 2, right? So if you have dimension 2, then you will have to do this thing which is called Voronoi diagram. And the Voronoi diagram will tell you over which region, right, you are closer to one point to all other points. But then you can imagine if you are at closest 3 points, then determining what are the regions of space in which certain 3 points are the closest point to this point, it becomes very, very tricky, right? So the shape of the region is going to be very complicated to determine. Okay, so remember the KNN is dumb in some sense, but searching through a data set will generally take you a complexity of n log n, and so some naive implementation of KNN will still be very, very expensive computationally. Of course, this method is very, very dumb because this search complexity increases with the size of the data set. So imagine that you have one of them, some sort of modern image classification data set where you have a few millions of images that, of course, you cannot, when you're trying to recognize a cat, you cannot sort through, let's say, tens of millions of image data set in order to find the closest picture of the cat to the cat picture that you provided to the system, right? So, of course, computationally, any trivial implementation of this will be suicidal. Then, when we talk about distance, it was always implicit for the discussion before that we're talking about the Euclidean distance. Of course, the Euclidean distance only makes sense in some setting. Maybe somebody could consider some other type of distance, some Manhattan distance, some Minkowski distance, some matrix distance. You know, L2 distance is only one of the options that we have in the big bag of distances that we can use. In this case, we are predicting a single number, right? So we are predicting the sales. Sales is a continuous number between 0 and plus infinity. You can imagine that instead we want to do classification. So, for example, we want to determine whether something is a male or a female, whether we are selling kitchen equipment or car equipment, something like that. In the case, it would be a different problem, which is a classification problem, and there will be some other mechanism to generalize this classification. As we said, it's very computationally expensive, so people figure out different ways to speed this up. More famously would be KD trees. If you guys have some background in computer science, you will know what is KD trees. Of course, this implementation, they suffer both from the dimensionality of the data set and the dimensionality of the data that we're using. And so people have to come up with some smart technique and some partitioning techniques to do this. So, for example, if you are doing classification between two classes, the red circles and the blue squares, then it's clear that we just have to keep track of the boundary between these two regions. So we could try to split this up with some restoring only the points that are meaningful in order for us to draw the boundary between the two classes. Okay, just some additional things for you to think about. Okay, linear regression. So here the tagline is that linear is equal to good. So as an engineer, whenever you see something linear, you know that you have the theoretical tools to tackle it. But of course, the other tagline will be linear is also equal to simple. So linear sometimes doesn't capture the complexity of the real world. Doesn't matter. So when we build our KNN model, we never chose the function that we wanted to use. Okay, we never chose this f of theta that we wanted to use in our statistical model. So we didn't explicitly describe this. So what we can do is that we can try to have a linear approximation. So we can say among all the functions that map the sales into the budget into the sales, we can choose this function to be a linear function, right? So we can say that the sales is going to be a certain coefficient B1 times the TV sales plus a certain constant plus a certain noise. And then we can go and try to find what is the best coefficient B0 and B1 that will specify our mapping between the sales, between the budget and the sales, okay? In order to do that, we will assume that there is a true relationship between the budget and the sales, which is a linear relationship. So we would have made a very strong assumption between the behavior of this. But once we do this assumption, then we can set up a mathematical problem that says, given the coefficients B0 and B1 hat, which are the closest coefficient to the true ones. And in order to do this, we have to add another ingredient to our story, which is the loss. Okay, we have to decide if the model is going to predict as y hat, and the true label in the data set is y. How are we going to decide the goodness of having y hat as the prediction, nor y is the true limit. Okay, and this is what we will call a loss, meaning that in this case, the sales, the predicted sales and the true sales, they are two real numbers. So we could try to measure their distance in the Euclidean space. So we can say, oh, well, the goodness of your prediction will be the Euclidean norm of the distance between y and y hat. Of course, if we were using some other type of data that maybe was discrete, that maybe was at a different type of range or a different type of behavior, then this Euclidean distance will not be good. And so we will have to decide another loss function. In this case, we are happy with the Euclidean distance. And so what we can do is that we can break down the prediction into the coefficient B0 and B1. And then we can say, well, the best B0 and B1 that we want to find are the one that minimize the loss function. So they minimize this sum of square distances, and the sum of square distances over our n. And remember that our beloved n is the number of elements in the data set. Very good. Then you go and you do some math, because math is it's always possible when you have linear models. And you say, oh, the best B0 and B1, which I call B0 hat and B1 hat, that I can find are obtained through this formula from the elements of the dataset. Let's look at this formula just because it's very intuitive. Remember that the summation is over all the elements in the dataset. So basically, we are saying the following. So B1 is sort of the slope of the line, right? B1 is the coefficient that control the slope of the line. B1 is this cross correlation coefficient, right? X minus X mean, Y minus Y mean. This very much has a feeling of cross correlation. And then what you normalize by the variance of the data, X minus X hat square. Okay, so this slope is very much reminiscent to your coefficient for finding the line between 2 points, to your correlation coefficient in statistics. And it's saying that this is the slope of the function. And then here, the B0 hat, as I say, it's an even simpler interpretation as the center of mass, meaning that we want that the line crosses by the average X. I mean to say this. If I choose my coefficient B1 hat, then I want that the line that B1 hat X plus B0 hat describes will pass by the point average X, comma, average Y. Okay, so if I choose the B0 in this way, then this coefficient, then this line, right, will pass by the average X, the average Y at the X value average X. So this, you can think of this as the center of mass, right? So very easy. So then there is some derivation. You can just go through this very quickly, right? So this is the expression. Remember, everything is scalar here, so everything is nice and easy. Y1 is a scalar, B0 is a scalar, B1 is a scalar, X1 is a scalar. We just take the derivative, the partial derivative of the loss with respect to B0, and then we set the derivative to 0. This is what we do to find the minimum of a function. We set the derivative to 0, then we check the second derivative. The second derivative is, of course, is always positive, so it's going to be a minimum. We find this expression, then we take the partial derivative of the loss with respect to B1. We set everything to 0 in order to find the minimum, blah blah blah. And basically, we find the mathematical expression of the minimum loss for the linear regression case. Okay, very good. So this is a very simple method, and there is a closed form solution. Never, ever again you will see a closed form solution for a minimization problem in machine learning. There are only 2-3 cases in which there is a closed form solution. In most cases, the solution is given in terms of an algorithm, an approximation, a procedure, something. The idea is that while this is a very beautiful result, it's very restricted in scope because the assumptions are very, very strong. But we can try to find some wiggle room around this limitation, meaning that First thing, we can do multilinear. So we can simultaneously predict multiple input dimension, multiple output dimension. No problem there. We can also repeat this to the case in which instead of having x, we can also x square, x cube, any polynomial of x. We can also manage it, because basically it's as if we create a data set with an extra column which correspond to the square of the x, the cube of the x, and then the solution goes through as expected. So something else that we can do is to try to teach to the model to be conservative. Okay, so if you look at this line, let's say, if you look at this line, you see that the B1 determines the slope. Let's discuss this for one dimension, then you believe me that the same will hold for a higher dimension. So if this B1 is large, you will see large variation of the prediction with X. Okay, this is undesirable. Okay, because in a sense, among all the models that you want to pick, you would like to pick a model that has conservative estimation, right? So you would like the model to have little variation in its prediction if there is little variation in the input. So let's call this sensitivity, right? So you will want the model to not be too sensitive, right? You will not want the model to change its estimation drastically for a small value of small variation of the input. And this corresponds to a value that you want to have this B1 small. Trust me, if you go to higher dimension where we have 15 inputs and we are predicting one output, then you will have 15 coefficients like this B1, and you will want all of them to be small. So what you can do is that you can add a penalty in the model for having large coefficients that multiply your input. And this is something that we call ridge regression. And the beautiful thing about this is that you teach a model to be conservative. So among all the possible functions that give you a good loss, you say, well, I'm happy to have a higher loss, but having a model which is more conservative in its estimation. I want to have a model that has a small sensitivity, as a small sensitivity to a small variation in the input. Be good. And then we can also manage other type of variables, right? So could have binary variables, binary variables. Okay, now so far we saw two beautiful things, which were the linear model and the L2 loss, and we found a closed form approximation. Of course, as you vary away from this, you quickly fall in the case in which there is no closed form solution. In particular, if you change the loss from the MSE loss to any other loss, basically, then you will not be able to find a closed form solution. So what you need to do is that you need to have an algorithm that solves the numerical maximization. Okay? So you will have that you are given a loss to minimize, and you put this into some machinery, and this machinery runs, and then spits out two values, and you will believe that these two values are sufficiently close to the true minimum of your loss minimization. The algorithm that we all love, because it's very robust, and it's very reliable, and it's somewhat easy to study, is gradient descent. Gradient descent, I believe that you've seen it already in your life somewhere, which is the following. You start from some random point. When you get to a certain random point, you calculate the derivative, and then you take a step in the steepest descent direction of the function. You take a step of a certain step length, which is part of your algorithm, and then you repeat this operation until you get to the point where you don't move much anymore. Okay? So the idea is that we start from here, we take the derivative, the steepest descent is there, we take a certain step, we repeat. When we apply this algorithm to the loss minimization, you will see that the loss minimization has to take the derivative of the loss for all of the points in the dataset. Here. You see here that we're taking the derivative with respect to the loss as summed over all the elements in the dataset. If your data set is hundreds of millions of images of cats, then you don't want to do this. You want to just take a subset of your data set element and just take a derivative as with respect to a subset of the elements in the data set, which means that you have to randomly select these elements in the data set in order not to bias your gradient evaluation. And when you do that, you have a stochastic version of the gradient, which approximates the two gradients over the data set. And we call this stochastic gradient descent, or SGD. Okay? Then you go on Google and you look for all the papers that the people wrote on SGD, and you will see a few million papers. Okay, because everybody loves the SGD algorithm. It is very reliable. It has done a lot for us, and it's a bread and butter of machine learning and deep learning. Okay, so if somebody asks you what is your favorite algorithm, let's say you go home to your family and your grandma asks you what is your favorite algorithm that you learned, you say, oh, grandma, I really love SGD. SGD is my bread and butter. Okay. Of course, the algorithm is prone to many errors and many mistakes and many wrongful approximation, because of course it is so simple that, for example, you start from different random points, you will end up in different random minima. So you're not guaranteed that the minima that you find is an absolute minima. So when your optimization space is very, very large, then you're going to have many, many different random minima. But this is the life that we decide to live. Okay, we prefer to find a very generally we prefer to find a very numerically efficient way of implementing SGD. And then we let SGD run for a very long time, and we restart it multiple times. And we're happy to pay the computational price to do that, because SGD is a very reliable algorithm that can really explore the space of solution in a sufficiently effective manner for a large set of problems that one encounters in life as an engineer. Now, there is something very important to discuss here, which is the confidence interval. Because what we discussed so far is the fact that we were able to find a model. That is, we were able to find the theta values that minimize the loss for a certain model when approximating the input-output relationship between your entries in the dataset. But this is sort of half of the battle, because knowing the model is not as important or knowing that the model can be is reliable. Okay. So let me give you an example. Somebody comes to you and they ask you for some money. They tell you, oh, give me $1 million and I will give you an algorithm that will predict the stock value from the value of Bitcoin from one day to the next day. And then you will not give them the money, okay? Because you do not know what is the quality of the prediction. If somebody comes to you and they ask you for $1 million and they tell you that they can predict the value of Bitcoin to within 10% of the actual value, then you are willing to pay a very large amount of money, right? So having a model, it is not important. Having a model for which you have a measure of reliability, it's what matters, okay? So models by themselves don't mean much. Reliable models are what we want. And how do we do that, okay? So very, 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 very significant question here. So let's say that we start, somebody gives us a model. And so what we do is that we evaluate the model for a certain set of points in the data set. And then we can see what is the error that is made by the model for these points in the data set. Okay, so we can calculate the model for a certain set of the values. So we have a certain estimation of this, but this is only part of the struggle that we have, right? Because what we see is the realization of the error over a certain subset of the points. We don't see a distribution, we just see some raw value. So in a sense, we have to try to argue that from the observation that we have, we can really say something about the precision of the model for a certain set of input, and this is not easy. So what we can do instead is that we can take another set of randomization, and we will obtain another set of errors. And then we repeat this a third time, and then we will be able to say, oh, well, we build a model, right? And for this model, we see this variation of the parameter V0 and V1. Okay? So let me say this again. Okay? So what we want to do is this is as follows. We want to have a model. We want to have an idea of what is the distribution of the error at different points of the model. So what we can do is that we can take the data set and randomly select a certain set of elements and repeat the fitting operation multiple times. Each time we will have a different fitted model, and we will have different f-hats, right? Every time we select a subset of the elements in the data set. And so what we can do then is to think that every time we select a subset of elements from the data set to fit the model, is as if we are in a different universe. And in all of this universe that we have, our estimation procedure gave us a different optimal V0 and V1. And so as you repeat this operation, you see that you build a distribution for the V0 and V1 values as you select a different subset of points for your data set. And this distribution will tell you what is the confidence that you have on your parameters in the model, okay? You will say that, well, in all the intervals that I looked in, I built the model, and if I look at the distribution of the parameters of the model, this distribution is sufficiently tight for me to be confident that the model is very robust, right? That really the model is very close to my optimal model. Okay? Good. So then we can say, well, for this model, we have mean variance, and so we can say over this set of parameters in my model, I have this mean variance, and if the variance is very large, then you know that you cannot rely too much over this parameter, so maybe you should drop it. And if you have a variance which is very small, then you know that there is a very clear relationship between the input and the output, between this input and this output, and then you can reason more and more about the statistical value of including or excluding parameters from the model. And remember that the beautiful things of these random procedures is that everything becomes Gaussian if you introduce enough randomness. This is the law of large numbers. And if you repeat this random procedure of selecting point and fitting models with enough randomness, with enough random operations, then you will observe a Gaussian distribution. And the beauty of the Gaussian distribution is that the variance decreases very, very quickly. Sorry, the tail probability reduces very, very quickly with the variance. So you know that if you are within 1 sigma, so within 1 variance from the mean, then that contains 68% of the probability. If you are between 2 sigma, right, from the mean, then that contains 95% of the probability. And if you're at 3 sigma, then it's 99.999. And so you know that the true parameter as estimated from the data, let's say, will be with 95% probability between 2 sigma of the value that you have estimated with this confidence interval. So if the sigma is very small, then you have almost certainty that the true parameter is going to be very close to the one that you have estimated. Very good. So let's say that we repeat this for our 2B and for our B1, B2, B3, which correspond to the newspaper, TV, and radio advertisement. And we see that we have these 3 different fitting of the parameters of the model over the multiple random selection of the dataset points over which to fit. And then you will see that, for example, here the variance is very, very small. So we are confident that the true relationship between the TV advertisement and the sales is there. And for example, this object, they have a very large variance, right? Maybe let's just say that this variance is very, very large. So we might decide that when we want to predict sales, we do not want to trust the value of the newspaper advertising because the influence of this input over the output of the model is too noisy for us to be trusted. Okay, very good. So let's do the last tick here, guys. I think we do a quick push. We should be okay. Yeah, we went a little bit long today, but okay. So support virtual machine. So this is for a different problem, which is classifying data. The classification means that you are deciding what is the label of a certain input to your model. For simplicity, we consider what the label is 0 or 1, just so that when we describe the classification problem, we just know that for each input we have to decide between a 0 and a 1. If you want to have more classes, then we can of course decide the generalization for this over multiple classes, but it's not particularly insightful to think about the general case now. So we have two classes, somebody gives an input, and we want to decide what is class 1 and class 2. And the thing with classification is that in general, how you separate the two classes, it's not unique. So look at the figure at the bottom here. The idea is that we have two input features, let's say x1 and x2, and then the label y corresponds to either 0 or 1. And for each of the points in the dataset, we can color the point with the label that it has. Right, so this is x1, x2, label 0. This is x1, x2, this is label 1. So if I just represent this in the dataset, there is no idea of minimality. There's no idea of unique minimum of this problem, meaning that I can put the barrier that separates the label 0 from the label 1 anywhere in the space, and this will produce the same labeling of the elements in the dataset. So we need to add some more criteria, which is well thought out, that will tell us how we should choose the distance, how we should choose the separator between the two classes. And this is generally not easy. Of course, again, we can go back to the idea of the minimality, right? We could choose the line that has the smallest coefficients. Maybe we look at this in some L1 or L2 norm, and we could say that this is as the purpose of giving us a robust decision boundary. But alternatively, we can consider some other geometrical consideration, which will give us a better guidance toward deciding what is the best line to use to separate these two sets. And the idea here is that we can talk about margin, right? So here we have two sets, right? And what we can describe is the distance between a set and a line, okay? And you see it here, right? So if this is the line that we pick, then the distance between a line and a set is the minimum between the distances as measured in the perpendicular direction of this hyperplane from each of the points of the dataset. So you see here that these are the distances between the line and the points, and the distance between the set and a line is the minimum of the distance between all of the points and the line. Then here we have two sets, so we can describe the distance of the line of a certain hyperplane between the hyperplane and the set of zeros, and the hyperplane and the set of 1, and we can choose the line that gives us the maximum minimum distance between the line and the points labeled with 0 and the points labeled with 1. Okay, very good. So this minimum will necessarily be the line such that it lies at the same distance between the set of zeros and the set of 1, so that we know that there is a sort of medium line that crosses by. And so the twice this minimum will be the margin. Okay, so you see here that we represent the margin. So among all the possible lines that we can choose to separate the set of zeros and the set of 1s, we choose the one that has the largest margin. Okay, so that this distance between the line and the points of zeros and the line and the points of 1 is maximized. Excellent, very good criteria to follow. So of course, reasoning one dimension is not interesting for us at whatever age we are, right? We are both a university, so we want to think about a higher dimension. So in higher dimension, we will, of course, discuss about hyperplanes and non-lines. The equation of the hyperplanes will be this vector equation, omega transpose times x plus b equal to 0. So we want to, we know that if this is the expression of the plane, then omega transpose represents the normal vector, right? So, sorry, omega represents the normal vector. So if omega transpose x is the coefficient of the plane, then omega is the normal vector from the plane. And then we can use geometry to describe the distance between the points and the plane along because we measured the distance along the normal plane. And this turns out to be this beautiful equation, omega transpose x plus b divided by the norm of omega. Of course, the norm of omega must be there, right? Because the line, right? If you multiply this omega by 10 and this b by 10, then the coefficient still holds, right? So this coefficient must be normalized by its norm, right? So when we take this normal vector, we should fix the normal vector norm to 1 so that everything is nice and properly scaled. Then we have to take the minimum of this object, right? So we want to maximize the margin subject that the distance is greater than the margin. And then we set up a certain set of numerical problems to solve this, right? So because we know that if we normalize everything properly by the margin, then we're going to find 2 points such that the distance between the hyperplane and this point is going to be equal to 1 for one. It's going to be equal to -1 for the other one. And we will call this as the support vectors because of the points of the decision boundary in which this equation holds. And then we just have to maximize this, right? So this is the closest point, which is a margin equal to 1. This is the closest point on the other side, which is margin equal to 1. The distance between the two is normalized to m. This is the normal vector. And, we set up a nice maximization problem, which we solve using some numerical solver. Okay? No point for us to discuss here the algorithm. Just be aware that these algorithms are very much studied in the literature. You can do something with SGD, but SGD is usually slow. People do some fancy things with some dual problem formulation, very, very fancy, nice numerical stuff. If you want to know more, take my other course on numerical recipes for ML. Okay, so good. So now things were easy now because in this case there existed a point, there existed a line that exactly separated the two sets of zeros and ones. And this happens if there is no noise, let's say, in your data, right? So if in your data you really have elements that are labeled zeros and one, and there is nothing else that influences the data, then the data is separable. But of course, maybe there is some data which is not separable. So if you look at this example here, if the data is let's say noisy in some sense or not ideal in some other sense, right? Then if you try to separate the data exactly, you might end up doing something like this. Here there is an outlier on your set of zeros, which is very close to a set of ones. If I try to separate it exactly, I might have a very skewed boundary where the margin between the two sets is very, very small. And the decision is some sort of unnatural because here we're just misclassifying one point. But in order to avoid misclassifying one point, you're paying a very high price. We will much rather prefer this situation in which we say, well, it's going to be a small number of times in which the algorithm cannot classify correctly some outlier. So some data point which is atypical in some sense, but I have a very good margin for all the points that I classify correctly. So this set up something which we call a soft margin, meaning that we minimize the margin plus a certain lambda for the errors, the times we make an error. We can manipulate this parameter as being an intensity parameter that tells us how unwilling we are to make mistakes during our prediction, very, very natural. And then we run the same set of classification algorithms and, same type of representation. Everything works out to be as we wish it. So if something is inside the margin, there's going to be an error of classification. We're going to pay a penalty for it, but we're going to maximize this Lagrangian sum of the mixed classification error plus the margin. And we manipulate how this goes, and then we just keep running this, and you can go through the slides, and you can see how the choice of discharge of lambda decides which behavior you should have with respect to your misclassification. Okay, and this is yeah. So this is the same plot as before. Yeah. So the thing is that once the merge has been decided, then you have to, given an input, you have to produce a decision, and this turns out to be very easy. But it's something that we're gonna meet next week, meaning that once we have a decision boundary, omega, right? Then if we have to decide whether something was classified as 0 or 1, what we will do is that we will take omega transpose hat, like omega hat transpose x plus b, and we're just gonna look at the sign, because the sign is gonna tell us if we are left or right of the hyperplane, and this is gonna tell us whether the sign is 0 or 1. Of course, here the sign operator will output -1 and +1. If the labels are zeros and ones, then we have to add a +1 divided by 2. Understand that? You understand the logic. Okay, good. So I think this part is not as interesting. Of course, the question is what happens if there is no good linear classification that one can do. And this is the typical case that people use to test this. This is called a spiral dataset for very clear reasons. And what people do is that they try to introduce some polynomial terms. As we said, even if we had polynomial terms, we can still run, let's say, our linear models as we did for the non-polynomial case. So if we had polynomial data, we can still run an SVM by considering, let's say, x squared, x cubed, x to the power of 4 as being extra data. So we can still try to tackle this. But in general, somebody would like to consider some higher space where maybe what appears to be a non-linearly separable problem might appear linearly separable. Okay, so for example, consider this mapping from R to R3. This is the polynomial space that we discussed before, right? So we have x, and we transform the single value x into the vector x to the 0, x to the 1, x to the 2. Okay, so we go from the space of dimension R to a space of dimension R cubed. And now, we can try to do the SVM over this higher space. And this is usually a very good trick when we have a problem. There is a non-linearly separable boundary, non-linear decision boundary, and we want to transform into a linear decision boundary. And this is the plot that you imagine, right? So in the input space, you have a very small dimension, but you do the mapping on a higher dimension so that what before you had to separate with a non-linear boundary, now you can separate with a linear boundary. So this is always the trick. If you want to make your problem simpler, either you consider the algorithm to be more complicated, or you augment the data input size, and you hope that a simpler algorithm on a higher dimension will do better than a complex algorithm at a lower dimension. Right? That's always a trade-off in life. Okay, it pays to stay in lower dimension. Yeah. Okay, very good. Now what we can do is we can choose any random function phi that we need, and we can try to augment phi from xj to xj prime. So sorry, we can try to augment x from xj to xj prime, and with the xj prime is much larger than the x, and then we can run things. And when you do this, you realize that in order for the SVM to work on this higher dimension, you do not need to calculate phi of j explicitly for the input in the dataset. What you can do is that you can run your SVM algorithm only memorizing the inner product between phi xm on the n of t and then n xm and the phi of xm. Okay, so if this j prime has a very large dimension, let's say this is 1,000,000, right? Then you would not want to store the projection of x of t to a very high dimension, because if your n is equal to 10,000, then you have 10,000 equal to 1,000,000 equal to 100,000,000. So a very large dimension. But if you store the inner product is only one number. So 100,000 by 100,000 is 10,000. So you will end up storing much fewer information if you, instead of storing the projection in the higher space, you will store all the inner products of your dataset points at a higher dimension. Okay, so this is the idea, because then when you run your SVM maximization algorithm, then you will just need to consider your the inner product in your penalty terms for calculating the margin, and this can be done very efficiently by simply storing the inner products. And this is what people call the kernel trick. Okay? The kernel trick is as follows: you choose the mapping file from J to J prime, but then you just consider the kernel of xn and xn, that is the inner product between this phi projection of xn and xn. Okay, and this potentially has a much lower dimension than storing the projection, by the way. Okay, very good. So I think we are good for today. This is something you can go through yourself. Again, just some introduction on machine learning. I just want to say the next time we're going to start from here, which is deep learning, and we're going to start from this beautiful picture, which is an artificial neural network. And we're going to say that we have an input x. We take a linear product with a certain set of weights. Then we apply an activation function, which is nonlinear, and then combining this activation function will let us express some very complex functions using very few parameters. And this is going to start our beautiful journey into deep learning. Okay, good. So let me know if you have any questions. Otherwise, next time we go through this material. So again, so whatever we did today was just for giving you a very brief introduction to machine learning. I'm not expecting you to study this or to do any homework for this. So this is just to give you a very quick introduction to machine learning, knowing that we will go to deep learning. If you want to do a little bit more reviewing, you can go see the videos on my channel, or you can look at the slides there. And otherwise, I'll see you guys next time. And I felt like I talked for a very long time, but probably, yes, yeah, it's just longer than usual. Okay, very good, guys. Any question, you let me know. Otherwise, I'm going to mute myself, stop the recording, and then you can either ask me a question, decide to leave, and we synchronize next week. Okay, ciao, guys.